Hello, everyone. Today, we introduce a method for embodied learning of reward for musculoskeletal control with vision language models.
Let's start with the motivation. In many control tasks, goals are easy to describe in natural language. For example, walk with good posture. However, translating these high-level descriptions into reward functions is quite challenging. This becomes even harder in high-dimensional musculoskeletal systems, which are nonlinear and highly redundant. Prior work often simplifies the problem by working with low-dimensional systems and relies on limited feedback signals. So the key question we hope to answer in this work is, can effective reward functions for complex musculoskeletal systems be learned from language and visual feedback?
To address this, we propose MoVLR, Motion from Vision Language Representation. This is an automatic reward learning framework designed for high-dimensional musculoskeletal control. The key idea is to leverage both language and visual feedback into the iterative learning loop, enabling the model to jointly reason over linguistic intent and physical motion. At a high level, MoVLR operates as a closed-loop system. At each iteration, a policy is optimized based on the current reward proposal, producing motional trajectories. These motion trajectories are then evaluated using a vision language model, which provides structured feedback. Finally, a language model uses this feedback to refine the reward function. This loop repeats, progressively improving the reward and the resulting task performance. The main workhorse of the MoVLR framework is multimodal feedback and reward synthesis. The first key component is motion language representation. In this step, a vision language model provides semantic evaluation of motion relative to task intent. The VLM operates on motion video and natural language goal descriptions. Specifically, it takes as input a motion video, task description, and video prompt, and produces a textual assessment of task performance. The second component is language-guided reward design. In this step, the language model translates semantic feedback into structured reward terms. The rewards are refined iteratively using the language model through the closed feedback loop. For this component, the inputs to the language model include the task description, the environment reward code, and the semantic feedback generated by the VLM. Based on these inputs, the language model outputs modified reward terms and code-level refinements that better align the learned behavior with the desired task objectives. Through this iterative process, semantic motion feedback is translated into executable reward modifications, enabling automated improvement of locomotion behavior through a closed feedback loop between motion evaluation and reward synthesis.
The evolution of reward term weights is a key factor to understanding how language models represent motion. This slide shows how the reward term weights evolve over the refinement process. At a high level, the weights are updated through feedback-driven refinement. And importantly, this evolution is structured and task-specific rather than random. If we look at the heat map on the right, we can see how different reward terms change in importance across stages. In the early stages, the model places more emphasis on global stability-related terms, such as maintaining height, balance, and overall posture. This helps ensure that the agent can first achieve basic feasible behavior. By the later stages, the reward structure becomes more specialized, focusing on coordinated and precise behavior. You can also see this progression visually at the bottom. From stage 1 to stage 15, the motion becomes increasingly stable and natural, demonstrating how the learned reward evolves to produce more realistic locomotion. We evaluate our method across a diverse set of musculoskeletal systems and tasks, capturing a broad spectrum of control challenges. The suite includes full-body locomotion environments, spanning flat, sloped, and rough terrains, testing the stability and adaptability under varying conditions. In addition to locomotion, the setup includes upper body manipulation tasks, such as bottle pouring and cube reorientation tasks, which emphasize coordination and precision, as well as a non-human locomotion task based on an ostrich muscle model to assess generalization beyond the human morphology. The performance of the full-body locomotion tasks are shown below. As shown in this slide, the method achieves successful locomotion across all three environments, demonstrating robustness to changes in terrain.
Looking at the reward term evolution in each case, we observe consistent and interpretable trends. The reward weights evolve in a structured way, adapting to the specific demands of each environment. The performance evaluation of the upper body manipulation and non-human morphologies are shown below. Compared to the locomotion tasks, these tasks require a combination of coordination, precision, and the ability to generalize beyond the standard human morphology. As shown in this slide, our method successfully learns effective behaviors across all settings, including both manipulation and the more complex animal morphology. Finally, we show the overall performance of our method compared to prior approaches. We compare against 3 baselines. First, human-designed rewards, which are manually crafted using domain expertise. Second, Eureka, an LLM-based approach that generates reward functions directly from text descriptions. However, it relies directly on text-based feedback and lacks visual grounding. Third, Harmon, which incorporates vision-language feedback but operates on limited visual inputs, such as image frames rather than full video, restricting its ability to capture temporal motion dynamics. Looking at the results for locomotion tasks in the top plot, our method consistently outperforms Eureka and Harmon, and in most cases approaches or surpasses human-level performance. In manipulation tasks on the bottom plot, we see similar trends, with our method achieving lower distance and orientation errors. Overall, this demonstrates that combining language with rich video-based feedback leads to more effective reward learning and improved control performance. To further visualize the improved control performance of our method, we compare MoVLR against a standard reinforcement learning baseline under the same training time budget. For locomotion tasks, a typical MoVLR round requires approximately 5 hours to achieve stable and natural walking behavior. In contrast, the reinforcement learning baseline trained for the same duration fails to reach comparable performance, exhibiting unstable gait patterns and poor task completion. This result highlights the sample efficiency and effectiveness of MoVLR, demonstrating how multimodal semantic feedback and language-guided reward refinement can substantially accelerate policy learning and improve motion quality. To conclude, this work proposes a multimodal framework for reward learning in complex control systems. By combining language and visual feedback, the approach bridges high-level task descriptions with low-level control through an iterative refinement process. Importantly, the learned reward functions are interpretable and structured, allowing us to better understand how the system improves over time. The method also demonstrates strong generalization across different tasks, environments, and even morphologies, highlighting its flexibilities. Future work will focus on improving the generation of more natural and human-like behaviors, particularly for complex coordination patterns and long horizon motion tasks that remain challenging for current reward learning approaches. Overall, this work shows the potential of using multimodal feedback to automate and improve reward design in high-dimensional control settings. Thank you for watching, and feel free to scan the QR codes to view our project page and full paper.